Yes.
There you go. Yeah.
Thank you. I think you can see my slides
Yes.
right now. Thanks for the introduction. I'm happy to be here, and yeah, it's right. I'm quite busy, so I have just these 20 minutes, and then I would need to leave to the next meeting. But I'm very happy to be here and tell you about Cryomotive's cryogas storage and refueling technology, which we believe is one of the technologies of the future for especially commercial vehicles, heavy-duty vehicles, coach buses, and further applications. So what is cryogas? It's a cryogenic compressed gas that can be produced by cryocompressing liquid hydrogen or by cryocooling gaseous hydrogen. It can reach up to 80 grams per liter physical density or more. It is very robust, so basically you can actually absorb a lot of heat. There is no evaporation, such as in liquid hydrogen, and with that you can realize very quick single flow refueling processes with no need to communicate between station and vehicle. Thermodynamically, I can try to explain cryogas in a density temperature diagram that shows the full range of cryogenic to high temperatures, ambient temperatures, and you see that the liquid hydrogen area is here below 33 Kelvin. There's the saturation line, liquid and gaseous, and the critical point at 33 Kelvin. And then there's the gaseous compressed hydrogen, which usually starts above minus 40 degrees centigrade, goes up to 85. That's the operating range of compressed gaseous hydrogen. And in between, we have the so-called cryogas, as we call it. And cryogas storage is basically a gas storage. It operates above the critical point. And it can be very cold and can also be quite an ambient gas. So the operating range is wide in terms of temperatures. And in terms of pressures, we tend to go up to like 50 megapascal, 500 bars, not any higher because the densities are high enough for everything. There, how do we produce cryogas? We pump liquid hydrogen. That's one of the two ways. And such a cryopump can then produce a cryogas above 80 grams per liter. We fill that into a tank, which brings a loss of density, a certain loss due to the heat of compression. This loss is not huge, so we still have something like 72 to 75 grams per liter in the tank. And that, all in all, is almost twice the density of 70 MPa compressed gaseous hydrogen at 40 MPa. In a truck, we see another opportunity. This technology had been developed by BMW at my time at BMW. There, the full operating range needed to be qualified because a passenger car is not operating a lot. It's parked, it has a lot of dormancy events. But in a truck operating regime, we expect that cryogas stays cold below 120 Kelvin, for example. So we have a very cold gas tank. We could switch to a warm operation, but regularly in typical operation, we may stay very cold. Where does the liquid hydrogen come from? You may have heard that today. I'm not 100% sure, but one of the options is that liquid hydrogen is a carrier of green renewable energy in the future. A few of these demo projects are already ongoing, and I have been part of this study here of the Hydrogen Council that forecasted in a very detailed clean room analysis process that liquid hydrogen may be imported to Europe at 3 to 4 euros already in the port. And from there, you can transport it to users such as a station and compress it to a cryogenic gas, for example. All that process may cost you another euro, so that we may end up at 5 euros per kilogram in the tank. So what exactly is cryogas once we have the liquid hydrogen at the station? If you bring liquid hydrogen to a station, which usually may be the case in large stations, so once you go 2 tons, 3 tons per day, it may be very hard to transport gaseous hydrogen into the station In such case, liquid with up to 4 tons per trailer may be a good opportunity. So once you get the liquid hydrogen in, you can actually produce 3 kinds of fuels. The first one is you pump it up to a very high pressure, such as 88 megapascal, and then you warm it up from cryogenic temperature to -40, and then you fill it into a high pressure gaseous tank. So the usable density in the tank is usually between 35 and 38 grams per liter. The second choice is you have a liquid transfer pump that pumps the liquid hydrogen into the tank, that may be in a range of 4 bars to 20 bars or so. And that would lead you to a usable density of something between 50 and 62 grams per liter, depending on your powertrain and preconditioning of the tank. Or you can use the cryopump, the same cryopump, for example, such as the one to the left here, to compress up to 40 megapascal and use the cold gas that you fill directly, and that would bring you to the highest densities, 70 to 75 grams per liter. So how to store such cryogenic gas? That's a technical challenge for sure, but it also shows some opportunity that I would briefly touch. It can be a very compact system. It can be quite lightweight. You can easily integrate that in multi-vessel configurations. It provides adaptive pressure supply to power fuel cells and hydrogen internal combustion engines at pressures above 10 bars or even 20 bars. It is quite robust in terms of thermal behavior, which also allows a simplified producible insulation concept, and it also is, as we believe, a cost-effective design. It's a moderate material and manufacturing cost to be expected. Here's an example of such a system. Usually, truck manufacturers like to have a frame-integrated vessels, so left and right of the frame. You could put the third vessel here, but 2 such vessels in typical truck configurations would be able to store 35 to 40 kilograms usable. So total, it could be even above 40 kilograms per vessel. And we can reach 8 to 10 weight% with such a system, very high volumetric density. On the insulation side, you may allow 20 to 50 watt heat leak, which gives you the opportunity to simplify insulation a bit. And still you can have a minimum holding time directly after refill in between 1 and 2 days. And the average holding time would be 10 to 30 days once you're 50% capacity. If you go below 35 to 40% capacity, your holding time is infinite, because then you are just a 40 MPa compressed gas tank. So you cannot get up to vent pressure anymore. There is different integration options for that system. You can go left and right of the frame. As I said, you can put the third vessel for very heavy duty applications, store up to 105 kilograms. Or you can also put an array of tanks behind the cabin of such a truck. And that would even lead you to 115 kilograms usable hydrogen. That configuration brings some challenges, though. So most of the truck manufacturers go to the frame integrated vessel configurations. There's some opportunities in any cryogenic storage. Basically, trucks have one big challenge if they have a fuel cell powertrain, is cooling. Very hard to have a fuel cell of 200 kilowatts or even more being cooled. So for example, when a truck's climbing very high load, the environmental cooling opportunities are limited because the speed is low. And the radiators may work at their limit, and still cooling is very challenging. So in that case, for example, you can use the cold energy from the tank and to support the cooling, add another 10 to 20% cooling power to the radiator cooling. So to summarize that, I think we have an opportunity here to store at very high capacities, 80 to 105 kilograms of hydrogen. For example, that would allow a range of 1,000 kilograms or more. There is an option for fast refill in less than 10 minutes. 8 to 10 kilograms per minute is our primary target such a refueling. Then you can deliver hydrogen at various pressures up to 20-30 bar if you want. And you could also use some of the cold energy to cool the powertrain, use a so-called cold energy storage if you want it. Then the fuel cell produces power for the motor, and that can be stored in the battery as a buffer. Quite flexible. In vehicle integration, you can do frame integration, you can do integration behind the cabin, or, for example, in a train on the roof, buses on the roof. So it fits to multiple long-haul vehicle configurations, truck, coach, bus, construction vehicles. Trains, we are currently developing an aircraft system, by the way. Also, that is obviously interesting. Smaller aircrafts may be a very interesting opportunity for cryocompressed because we have very high density and also a very simple refueling method. Good. With that, I already summarized the storage opportunities. So basically, that's the applications that we look into. First is long-haul heavy-duty trucks. It's a big market. May need hydrogen. Coach buses will have a lot of similarities, so they may use the same powertrain. Trains are a limited opportunity here in Germany, especially in Europe, because we still have diesel trains that may be converted. It's not a prime focus for us now. There's farming machinery, again, that may be coming at a later point in time. Interesting for us is really the small aircrafts, the urban air mobility options, and the smaller aircrafts, and huge heavy-duty construction vehicles or other vehicles such as garbage vehicles. That's an application or applications that we have in mind. Now let's come to the refueling, which is the second part of this presentation. So how do we refill? I already said that we may refill from liquid hydrogen or from gaseous hydrogen, and that allows us to leverage synergies with an existing 350 bar infrastructure. Let me give a few details on that. So you can basically use so-called cryopumps and for example use liquid hydrogen trailers as storage or stationary storage as well, and then you pump a cryogas by a submerged liquid pump into a truck storage, and that allows you to be filling 75 to 85 grams per liter in less than 10-15 minutes. Or you can deliver gaseous hydrogen, which may be an interesting option in decentralized electrolyzers that we have here in Germany. And you can cryocool this gas down to high densities of 58 to 68 grams per liter. The interesting aspect of the cryocooler is it needs much less energy than liquefaction, so it is more energy efficient. The overall energy pathway may therefore be more energy efficient, and that could be an interesting option, at least in a transition time, to convert such stations from gaseous direct refill with an upgrade of cryocompressed refill for long-haul heavy duty. Such a station can be very compact. Now that's the liquid delivery station again. It can be energy efficient and the connection power may not be high. We believe it's very safe because it doesn't have any high pressure buffers. If you have a direct fill, it may be very fast to fill, and also cost effective design is something interesting. Please have a look at the refueling system here that has been developed at BMW at the time jointly with Linde, as you can see. That's a nozzle of Walter. We will actually redevelop such system. There will be a new heavy-duty nozzle being available next year for first prototype testing. That nozzle will allow us to fill around 250 grams per second, so 13 kilograms per minute. We have no communication included into the nozzle, but have a few interesting options such as air purging, leak monitoring, and freeze protection. So that's the station here. One of the concepts that has a liquid supply. So we imagine that with two trailers connected, you can allow 3,000 to 6,000 kilograms per day. There's a buffer system. Then there is a cryopump with its safety measures, and the cryopump would directly compress to cryogas, and that cryogas through the new nozzle and dispenser that we currently develop would allow 250 grams per second, a 30 to 40 MPa pressure at the temperature that you see here. The second station type that I would like to show is a small station type where you have just liquid hydrogen supply by trailer. You have a stationary buffer, and then you have a small pump that, for example, only does 200 kilograms per hour, which is available in the market right now. And such a pump could then use cryo-compressed cryogas buffers to store, to buffer a cold gas, and with an expander, then really fuel that into the vehicle. So that would be a very compact, small station that may be integrated in the early stage once the station capacities are still low. And then finally, there's another option which we investigate is we could actually deliver cryocompressed gas to a station. So we use insulated pressure vessels on a trailer and transfer the cold gas at high density already to the station, where we only need a cold gas compressor that could be very effective. This is still an R&D project, but we look into it. Again, the buffers could help to then have a very quick refill. This option allows us, for example, to use a decentralized green hydrogen pathway. You have an electrolyzer, you cool down the gas to cryogenic temperatures, you fill the cryocompressed gas into cryogas trailers, you bring the cryogas to the station, and then you compress into the vehicles. You could also use that for very effectively fill 35 MPa compressed gaseous storage systems, for example. And if our analysis reveals to be correct, then maybe this would enable us to have stations with trailers of capacity up to 2 or 2.5 tons, which allows us a more effective delivery scheme. Good. That's almost all about what I can tell you today. So we developed that system and want to deploy the first storage system into trucks in 2023, 2024, then want to go into small series applications in 2024, 2025, and by 2026, we believe this can all be scaled up on a station and storage level. Yes, so I think I'm happy to have this opportunity here to present you Cryomotive's very ambitious technical roadmap, and I'm open for a few questions if there are any. Thank you.